Imagine you're sitting at a restaurant waiting for your food and you're really bored. So you start picking up a toothpick and dropping it over the table, over and over again. Your friend looks at you like you've just lost it. But what if that mindless thing you're doing is actually one of the most elegant probability experiments in the history of mathematics, and it somehow leads straight to pi? This is called Buffin's needle problem, proposed by French mathematician Georges Louis Leclerc back in 1733. The setup is almost identical to what you were just doing at the table. Imagine your table had parallel vertical lines drawn straight on it. They're all equally spaced. You can call that spacing d. Now your toothpick also of course has a length, and we can call it L. Now every time you drop it, it lands at some random position and angle relative to those lines. The question now is, what is the probability that the toothpick actually crosses a line? To figure that out, you need to track two things about where your toothpick lands each time. S is the distance from the center to one of the lines, and theta is the angle that the toothpick makes with the line. Since the center can land anywhere between a line and the midpoint, your S value ranges from 0 to d on 2, or half the distance between the two lines. And your theta runs from 0 degrees to 90 degrees, or in other words, pi on 2 radians. If you put pi on 2 radians into a calculator, you get 90 degrees. So when does your toothpick actually cross a line? Since the lines are vertical, only the horizontal reach of your toothpick matters. By basic trigonometry, that reach can be represented using the expression L on 2 times the sine of theta. Your toothpick crosses whenever its center is close enough that the tip can reach the line. This can be represented using the inequality S is less than or equal to L over 2 times the sine of theta. Every single drop you make either satisfies that inequality or it doesn't. That's the heart of this whole problem. When your point falls below the curve S is equal to L on 2 times the sine of theta, your chopstick crosses a line. When it falls above, it misses. This means that the probability of a crossing is equal to the area under the curve divided by the area of the rectangle. Now the rectangle's area is easy. You have pi on 2 and d on 2, and you can just multiply them together. When you multiply pi on 2 times d on 2, you get pi d on 4. Now for the area under the curve, there isn't really a conventional formula that you can use. Instead, you need calculus. Now the area under the curve S is equal to L on 2 times the sine of theta from 0 to pi on 2 can be represented using the integral of L on 2 times the sine of theta d theta from 0 to pi on 2. Now this does look quite scary, so I'll tell you what all these parts mean. This L on 2 represents half the length of the toothpick. This sine theta is the component of that half length reaching the line. Now this d theta, this little chunks of the curve with lengths of d theta. When you add up all of these little chunks, you get an approximation of the area under the curve. This goes from 0 to pi on 2. Now we can simplify this. We can pull out this L on 2 to get the integral of sine theta d theta from 0 to pi on 2. This entire thing is multiplied by L on 2. Now there's something called as the antiderivative. This applies to the sine theta. The antiderivative of sine theta is always equal to negative cos theta. This means that you can find negative cos theta from 0 to pi on 2. Then you subtract this upper limit from the lower limit. Now negative cos of pi on 2 is equal to 0, and negative cos of 0 is equal to negative 1. Now when you subtract the upper bound from the lower bound, you get 0 minus 1, which is just equal to 1. Now when you multiply this 1 times the L on 2, which we just pulled out earlier, we get L on 2. This L on 2 represents the area under the curve, which represents every drop where you get a crossing. Now if you remember the probability formula, it is the area under the curve divided by pi d on 4, as that is the area of the rectangle. Now we sub in the area under the curve, which is equal to L on 2, and we get L on 2 divided by pi d on 4. This simplifies neatly to 2L on pi d. This is the classic Buffin's formula. Now we get the special case, where the length of the toothpick equals to the line spacing. In other words, L is equal to d. We can give these a value. Let's say that L is equal to 3, which of course means that d is equal to 3. When you sub in 3 into the Buffin's formula, these 3's in the numerator and denominator cancel out, which means that you get 2 on pi. This approximately equals to 0.637. Multiplying this by 100, you get roughly 64% of the time the toothpick lands on a line. But here is where you can actually calculate pi. You can rearrange this equation for pi to get pi is equal to 2 times the number of drops divided by the number of crossings. Every time you drop that toothpick, you're running a step in a pi calculating experiment. The more you drop it, the closer your estimate gets. We usually associate pi with circles, and that makes sense because to find the area of a circle we use pi r squared, and to find the circumference we use pi d. But this experiment has proven that you don't really need circles to find pi. Pi didn't need a circle at all. It just needed you to be bored enough to drop a toothpick.